Okay, so let me add like a famous problem. This is basically either or, is not like inclusive or, is or, is like just A or just B, not A and B together. And geometrically speaking means that if one is true and zero is false, or like in this case, like, above the axis, like positive is true and negative is false, the solution of this problem is this quadrant here and this quadrant here, not like they are not non-contiguous regions. And this is a famous problem because this thing, you can see immediately, is not linearly separable. Like, I will never find a line that separates, like I can draw here that puts the two blue areas together, separate from the two orange areas. So my softmax here has a few problems. If I do the same thing with my new data, this thing has a few problems. It will try, but has few problems figuring it out. Yeah, so this is like I created like a difficult problem for my net to solve. So this is basically unsolvable with the linear model, and so I need to move to nonlinear to solve this. And there are several ways to do this, and I'll do a couple just to show you a bit ways to do things. The first one is that I directly, encode some knowledge of the like my private human knowledge of the world into the model. So, for example, this is going to be the tour, and then we come back to the XOR later. Let's say that I, in the typical linear combination, I know that my problem is something like this. Here is a combination of a constant term, a linear term in two variables, and a non-linear term like a square term. And these are all sum with this linear combination of values, and I have some random noise here, like uniform noise. Now, a way to solve this problem with a linear system is to say, I know that I can have these functions, the xy to the power of 0, x to the power of 1, x to the power of 2, y to the power of 1, y to the power of 2. And then I let my linear model find the coefficients of this. Yeah, so I define like an encoder function, something which is transforming my x and y in more values. And now my input, my encoded input is not 2 values, but is in this case is 5 values. So I kind of inflate my input space, and I can do something like this, attach it to my model with this encoder function, net encoder. I put my function inside, and I say, this is an arbitrary function, so I give some constraint to the framework for size inference, and I say this is going to be a size 5 vector. And then this works exactly the same with the difference compared to this, that I can attach it to my to a neural network. So here, for example, I say that my input is the encoder, and here I only specify the output because the input is inherited, and I say it's a real number. So now this is a network that takes an expression, like in this case it's 2. It explodes it to 5, and then compacts it to 1. So this way, yeah, this is a. I mean, SVM is actually is not doing this explicitly, yeah, because SVM is using the kernel trick. So you are never really explicitly computing this stuff. You are only computing the dot product in a high dimensional space. Why I add the y square term? Well, this was to be a bit more neutral. Like, let's assume that I'm not, I know that it's a quadratic problem. I don't know the value of the coefficients. Here I put, all the terms. A good model will say that the coefficients of y square is close to 0. Like either 0 or like typically close to 0, and you can filter it out as a post-processing step. So yeah, no particular reason. I just wanted to be a bit more neutral compared to the nature of the problem. Okay, so this is one way to do it. And using this thing, you can, in this case, I'm encoding a quadratic problem. You can encode completely different objects like images, for example. So here, I have an encoder that takes an image, and I want it to be like an RGB image, and I want it to be a 5x5 matrix. So you see it says type image output array, and if I attach something like this to a network, I get a network that takes images as input. Yeah, so you see that the kind of quality of life here is that you can attach these things at the input and output, and then use your functions like it's a function that takes an image in, and we have an image object in the language. So you see, if I apply image encoder to this becomes a list of matrices. This is what is called the non-interleave format, where the channel is the first dimension. I have channel, height, and width. And basically, this representation now has no relationship. It's not an image object. It's no JPEG stuff there. This is just a tensor. And so my encoder is a bridge between the kind of image word and the tensor word that the networks understand.